Hey, this is Ana Doblas with the first video of the module Wave Optics for the course ECE 513 Intro to Optics and Photonics. In this class, we will define a wave optics as a wave function that needs to satisfy the wave equation. We will identify wave equation form for waves traveling in any media. We will understand the superposition principle. We will define the optical intensity and the power, introduce a monochromatic wave, and understand that the complex amplitude satisfy the Helmholtz equation. So in wave optics, we have three postulates about it. The first one is related with the wave equation. So every time that we are talking about an optical wave is going to be defined by a real function that is going to depend on the three-dimensional position and then the time. The wave function needs to satisfy the wave equation, which is going to be related where we call it as a partial difference equation because we have there the Laplacian operator, which is the second derivative with respect to the space, and then the partial derivative of the wave function with respect to the time. So if you notice on the wave equation, we have 1 over the velocity squared, right? So in general, this wave equation is valid for any medium, just like depending on the refractive index, you're gonna be changing the velocity that you need to satisfy on the wave equation. So the second principle in wave optics, it's about the superposition, right? So basically what you are saying is like, let's assume that you have two waves with two different wave functions that they meet in the same space and at the same time. So we're gonna talk about a resultant wave function that is gonna be the summation of both of them. And that's just gonna say that the same time that we are each of the wave functions satisfy the wave equation, the resultant wave function should also satisfy the wave equation. So this is telling us that the wave equation is linear. The third postulate is talking about the properties, how when we are saying how intense or power is the wave, is the intensity of the light. So we're gonna define the optical intensity as the average over a temporal interval of the modulus square of the apse of the wave function. Once we know what is going to be the optical intensity, the power is just the integrated intensity with flowing in a particular area. So if you cannot notice, because we have the average over the temporal interval, the intensity is not going to change with the time. And then the power is the one that is going to be invariant because it's going to be related with a particular space, a particular area. Alright, so let's talk a little more about monochromatic wave. So we talk about monochromatic wave as those wave functions that they are harmonic with respect to time. So that means that they follow a periodic behavior with respect to the time. And typically we put that periodic behavior expressed as a cosinusoidal or sinusoidal function. So when we are talking about monochromatic wave, we need to define our amplitude. We need to define the periodicity, right? So we're gonna talk about the frequency, and the temporal period is gonna be 1 over f. We can sometimes define it as omega, but also we can talk about any initial phase, such as for the time equal to 0, the value is not going to be maximum, it's going to be some delay on it. And if we define the monochromatic wave as a cosinusoidal or sinusoidal function, then the intensity of the monochromatic when we perform the average with respect to time across a period, that's going to be just only the amplitude of the square of the amplitude, because we have assumed that the amplitude here it's real. So We know that the wave function of a monochromatic wave is cosinusoidal. So that means that we can talk about as the real part of a complex function, right? So we can define now, instead of our real wave function, we can define our complex wave function, where we have assumed here that our amplitude is also complex, and then the exponential associated with the periodic change with respect to the time. So if we are working with an optical wave function, our real wave function needs to satisfy the wave equation. So in this case, our complex wave function must also satisfy the wave equation, right? What is gonna happen? So we talk about the wave function, the complex wave front, the solving for the wave equation. But now we were saying that the complex amplitude, where is gonna be the equation? So for the complex amplitude, what the optical wave needs to satisfy is what is called the Helmholtz equation, where now the periodicity that we're gonna have here is with respect to lambda, and we're gonna define the parameter k that talks about the wave number. So just a little summary about it. So a wave is defined with a wave function that needs to satisfy the wave equation, and remember that that's a partial differential equation, where here we have the derivative, the second derivative with respect to time, and here we have the partial derivative with respect to time. And sorry, those ones are respect to the space. Then monochromatic wave have a constant frequency and follows a periodic behavior, so it's gonna be well represented with a cosine or a sine function. Just remember that cosine or sine is the same behavior, just a delay of pi and a half. The monochromatic wave, if it follows a cosine, the cosine we know through the Euler equation that it's the real part of a complex exponential, so we can define the complex wave function, introduce here our complex amplitude. So the complex amplitude, it needs to satisfy the Helmholtz equation.